Now we're going to start looking at another special kind of sequence called a geometric sequence. Geometric sequences are dealt with in section 13.3, and they involve multiplying or dividing by the same number over and over again. So there are a lot of comparisons we can make between arithmetic sequences that involve adding or subtracting and geometric sequences that involve multiplying or dividing. So let's look at an example. Suppose we start with a given number, and I just pick 30 at random, and then we multiply by the same number over and over again to get an infinite sequence. So let's just say that we multiply by the number 5. And the sequence that we're going to get is 30, our first number, then 30 times 5 is 150, times 5 again is 750, times 5 again is 3750, and so on and so forth. So this is an example of what's called a geometric sequence. In our example, a sub 1 is 30, a sub 2 is 30 times 5, and so that 30 times 5, that's just our 150, right? A sub 3 is that 30 times 5 again, which can be thought of as 30 times 5 squared, that's the 750 value. A sub 4 is 30 times 5 times another 5. We keep multiplying by an additional 5, so we can think of this as 30 times 5 to a power. For a sub 4, it's 30 times 5 to the third. That's going to be 3750. And then the pattern continues, so a sub 5 is 30 times 5 to the fourth power, and that's turns out to be that 18,750 number. Things are getting large here. And so we can write this as a formula now so the geometric sequence will have its own kind of formula, and it's very different from the look of the arithmetic sequence. So we can say our a sub n is equal to that. It's always going to be that first term, 30, times a power of the number that we keep multiplying by. And that power is always going to be 1 less than the subscript on the term. So a sub 5 involves 5 to the fourth power. So we can represent that in our formula by writing an n minus 1. And it's kind of like n minus 1 because the first term doesn't have any 5s, and we get our first factor of 5 when we're already to the second term. So the factors of 5 are always sort of like one behind, right? So here's a general formula for the example up above. And we can also just make a more general statement about geometric sequences. If we let a sub 1 and r be real number constants, any numbers, then any sequence of the form a sub n equals a sub 1 times r to the n minus 1. So think of our example. That was a sub n equals 30 was the a sub 1 times 5 to the n minus 1. 5 is the r value. That's called a geometric sequence. A sub 1 is the first term of the sequence, and r is called the common ratio. And we'll talk more about why we call it that as we go through our examples. So again, in our example, a sub 1 was 30. The common ratio, r, is 5 in that example. So let's go ahead and do some exercises now. So let's determine in number 1 if the sequence is geometric. If yes, find a common ratio r for the sequence. So in a geometric sequence, we get from one term to the next by multiplying by the same number over and over again. And if we're saying 5 times what is negative 5/3, I can figure out what is by taking negative 5/3 and dividing by the term before dividing by 5. So I'm actually going to take negative 5/3 and divide by 5. That's negative 5/3 times 1 over 5. The 5's will cancel, and I end up with negative 1/3. And so 5 times negative 1/3 is negative 5/3. Now I have to see if that same number keeps working all the way down the line. Now notice, because I divided one term by the preceding term to get that negative 1/3 constant, that's where the name common ratio comes in. Ratio, the word ratio is related to division. So now I'm going to take 5/9 and divide by negative 5/3, and that's 5/9 times negative 3/5. Now the 5's will cancel. I get negative 3/9 or negative 1/3, so that works here. And again, I could also just try multiplying and checking all the way down the line, by the way. If I take negative 5/27 and divide by 5/9, see, the 5's will cancel, a 9 will cancel, I get negative 1/3 again. So far so good, times negative 1/3. 5/81 divided by negative 5/27. It's 5/81 times 27 over negative 5. 5's will cancel, and a lot of factors of 3 will cancel. I get negative 1/3 again. So it's still working, times negative 1/3. And one last one to check. And I'm going to let you verify this. This also comes out to be negative 1/3. It does work. And so the answer is yes. This sequence is geometric. And the common ratio R is equal to negative 1/3. All right, let's go ahead and do another exercise. Now let's look at exercise 2, determine if this sequence is geometric. And since I'm being nice to us here because our fractions were so ugly in that previous one, here I'm just asking myself 5 times what is 10? I actually can do this in my head, right, without even dividing. 5 times 2 is 10, I can see that. 10 times 2 is 20. 20 times 2 is 40, so far so good for being geometric. 40 times 4 is 160. So there is no common ratio. The sequence is not geometric. And again, if it's no, that's all we gotta say once we verified that we don't have a common ratio down the line.